Good evening. Am I audible? Samaira?
Yes, sir.
Okay. So in last class, I defined expansion of solid along its length. That is called linear expansion. And I defined its application related to biometric strip till this part. Next application of that linear expansion is pendulum clock. Suppose there is a clock which is configured to run on oscillation of pendulum. So on going from this point to this point, it takes 1 second, during which this second hand will move just by 1 second. On returning back to this point, it will take 1 second. So reading in this particular clock will be just 1 tick. So for this pendulum or simple pendulum, we may define its time period t equals to 2 pi root under L by G. Initially, at some temperature T naught, time period will be T naught, and length of this particular pendulum is L naught. So if you change the temperature of this surrounding, length of bob or length of rod, that is this part, I have just assumed to be metallic, may get changed. So on changing this length, time period of oscillation of pendulum will also change, and hence the reading of clock will change. So we have to calculate how reading of clock would be affected with change in temperature. Is it clear?
Yes, sir.
Suppose at temperature T, length of pendulum will become L naught 1 plus alpha delta T, where alpha is coefficient of or temperature coefficient of linear expansion and delta T is change in temperature. So final length of this pendulum will become this. So if you put this term in the above formula, so time period of pendulum will become 2 pi root under L by G. If you substitute the above value in this expression, you will get 1 plus alpha delta T divided by gravity. Now we have to calculate relation in between these two parts. Let's say this is equation first and this is equation second. So on dividing, T divided by T naught equals to 2 pi root under L naught 1 plus alpha delta T divided by G whole divided by 2 pi root under L naught by G. So 2 pi and 2 pi will cancel out. L naught by G, L naught by G will cancel out. So you're left with 1 plus alpha delta T whole to the power 1 by 2. Now, according to binomial expansion, we may write this expression as, since 1 plus x raised to n will become 1 plus n times of x, so this exponential half will get multiplied with the coefficient of alpha delta t. So you'll get t divided by t naught equals to 1 plus half delta t. Now move one to left side. So you'll get T divided by T naught minus 1 equals to half alpha delta T. Now take LCM of this particular part. So you'll get T minus T naught divided by T naught equals to half alpha delta T. So this particular difference in time will define you amount of time lost or gained during a period of interval if there is change in temperature of surrounding. So we may write this expression as delta T equals to half alpha T naught delta T as final expression. Asma, is it clear? Okay, first write it down till this part. Then I'm defining you different problem related to this part.
Done, sir.
You all have done?
Done, sir.
Shikha, Nahra, done?
Yes, sir.
For this last expression, let me define you its different part. In this part, delta T simply defines you amount of time loss or gain for a particular period of time if you calculate. So this delta T simply defines you gain or loss in time on changing temperature. Alpha is temperature coefficient of linear expansion. It simply defines at what rate length of a particular object will change on changing temperature of surrounding. T naught is time for which we are calculating. So this will define you duration of time, and delta T is temperature difference. So on the basis of this formula, let me give you a question. A pendulum clock gains 4 seconds in 1 day at 20 degrees Celsius and loses 12 seconds in 1 day at 40 degrees Celsius. So find temperature at which it will show correct reading. Let me define you how to simplify this part. First, write it down, the above expression and then this question. Okay, you all have written?
Yes, sir.
Asma? Okay. Suppose you have a clock which is configured to work at some temperature T naught, so that at this temperature, its time period of oscillation of pendulum will be T naught. Now, if temperature of surrounding is changed, let's say temperature is increased. So on increasing temperature, length of pendulum will increase according to the concept of linear expansion. So on increasing temperature, length of pendulum increase, and according to the formula, T equals to 2 pi root under L by G. Since time period of oscillation of pendulum is directly proportional to root of L, so on increasing temperature, increasing in length will tend to increase its time period. So initially, on going from this point to this point, the time of oscillation from one end to another end is 1 second. But now, on increasing length, it will take 1.1 second. Suppose for this period of time, clock will read just one tick, which will be 1.1 second, or it will be just 1 second according to the reading of clock. Similarly, on going back from this point to this point, it will again take 1.1 second. So reading of clock for this time would also be just one tick. So in total, this clock will read just 2 seconds, but in actual duration of time in total would be 2.2 seconds. Is it clear? Let me explain you once again. On increasing temperature, length will increase according to the concept of expansion. And since length is directly proportional to time period of oscillation of simple pendulum, so time period of pendulum will increase. So initially, it was just 1 second to go from one end to other end. But now on increasing its length, time period increases. So it may take 1.1 second to go from this end to this end. So in this particular duration, this clock will read just 1 second, since the reading of clock will depend only on oscillation part. That is, if length or if this pendulum moves from this end to this end, it will be counted by just 1 second. But in actual, it is taking 1.1 second. Similarly, on returning back to this end, it will take 1.1 second, but this clock will read just one tick. So in total, time taken or time calculated by this particular clock will be 2 seconds, but in actual duration of time taken by this pendulum to go from one end to this end and returning back is 2.2 seconds. So we can say reading of clock in this part will be decreasing, or you can say there will be some loss in time in reading of this particular clock. Is it clear?
Yes, sir.
Sakshi, is it clear? Samaira?
Yes, sir. Yes, sir.
Okay. So we can say on increasing temperature, length of pendulum increases. So time period of pendulum increases. So reading of clock decreases, or there will be loss in time. So in this part, delta T will define loss in time. Similarly, in next part, if temperature of surrounding is decreased, so on decreasing temperature, length will contract, so length will decrease. Correspondingly, time period of simple pendulum will also decrease. It means initially it was taking 1 second to go from one end to the other end. Now, due to decrease in length, let's say it would take 0.9 second to go from one end to other end. And similarly, on returning back, it will take 0.9 second. So in total, actual duration of time would be 1.8 second. But for this entire period, clock will read just 2 seconds. Since reading of clock is depending upon oscillation or going from this end to this end only. So in this case, we can say reading of clock increases. Is it clear?
Yes, sir.
There will be some gain in time for this particular period. Nahara, is it clear? Samaira, any doubt?
No, sir.
Okay. So according to the above question, a clock gains 4 seconds. So in which case it will gain some amount of time, first case or second case? When temperature is decreased. So this particular temperature will be smaller as compared to T naught. So we can write delta T equals to half alpha. T naught is duration, which is 1 day, and temperature difference will be T naught minus 20 degrees Celsius. In next part, it loses 12 seconds in a day at 40 degrees Celsius. It will be first case when temperature of surrounding will increase. It means delta T equals to half alpha T naught, that is duration of time, 1 day, temperature difference 40 minus T naught. Now we have two different equations, this and this. Just divide these two equations and simplify it to find T naught. Is it clear?
Yes, sir.
Try to solve. Suppose if you divide these two equations, 12 equals to half alpha 1 day, temperature difference 40 minus T naught, whole divided by 4 equals to half alpha 1 day, temperature difference T naught minus 20. So on simplifying, this part and this part will cancel out. So 12 in 3 times. Now on cross multiplication, you'll get 3 times T minus 20 equals to 40 minus T naught. So 3 times of T naught minus 60 equals to 40 minus T naught. Move T naught to one side and constant part to other side. So you'll get 3 T naught plus T naught equals to 40 plus 60. So this will become 4 T naught, 40 plus 60, it will become 100. So from this part, T naught will be 25 degrees Celsius. Is it clear? Samaira?
Yes, sir.
Shikha? Sakshi? Any doubt?
No, sir, no doubt.
Okay.
Done, sir.
Nara, done? Sakshi?
Yes, sir.
Okay. This is all about linear expansion and temperature coefficient of linear expansion. Let me define you the next part. Superficial or areal expansion. Suppose you have a rectangular sheet having initial length L naught and breadth B naught. So on increasing temperature, expansion of this particular object will be uniform along its all side. So length will increase and correspondingly breadth will also increase. So in general, its area will expand up to this part. So final length will become L and final breadth will become B. So if you have to calculate how rate of area is increasing with change in temperature, so we may define a quantity which is called beta, which is temperature coefficient of areal expansion. It simply defines at what rate area will change with change in temperature. So it defines the rate of change in area with respect to change in temperature. So according to this, we may write this beta as beta equals to delta A divided by A times delta T. So in this part, delta A divided by A is called fractional change in area, and this delta T is called change in temperature. So we may define this beta as the ratio of fractional change in area to the change in temperature. So this beta is the ratio of fractional change in area to the change in temperature is called beta. Now, change in area and original area will having same unit meter square, so they will cancel out. So we're left with just delta T, which is in denominator. So SI unit of beta will be Kelvin inverse or degree Celsius inverse. Is it clear?
Yes, sir.
Asma, any doubt? Okay, just write it down to this part.
Done, sir. Done, sir.
Arslan, Sakshi, done?
Yes, sir.
Okay. Now, if you expand this particular formula, since beta equals to change in area divided by initial area times delta T. So move this denominator to left side. So you'll get delta A equals to beta times A naught delta T. Delta A is nothing but change in area. So we may write final area minus initial area equals to beta A naught times delta T. Now move this A naught to right side. So it will become A equals to A naught plus beta A naught delta T. Now take out A naught as common. So you will left with 1 plus beta delta T equals to final area. So this will be expression of getting area at any instant on changing temperature. Samira, is it clear?
Yes, sir.
Okay. Just write it down.
Done, sir. Done, sir.
Nara, any doubt?
No, sir.
Okay. Now, first question is how to relate beta with alpha, or what will be relation between alpha and beta? Alpha is temperature coefficient of linear expansion and beta is temperature coefficient of aerial expansion. So let me define the relation between these two terms. Since A equals to A naught 1 plus beta delta T, According to the above part, what we have derived, let's say this is equation first. Now, according to expansion along its length and breadth, we may write length equals to L naught 1 plus alpha delta t, since length is a one-dimensional expansion or expansion along its length. Similarly, breadth will be also treated as length, so it will be b naught 1 plus alpha times delta t. So if you multiply these two expressions, you will get area, which is nothing but product of length and breadth. So on multiplying these two above part, you'll get L into B equals to L naught 1 plus alpha times delta t multiplied by B naught 1 plus alpha delta t. Now L naught and B naught times 1 plus alpha delta t, having raised power 1 at this point and raised power 1 at this point. So on combining, you will get alpha 1 plus alpha delta t raised to 2. Now, according to binomial expansion, 1 plus x to the power n will equals to 1 plus n times x. So using this expression, we may write this length into breadth as final area, this length into breadth as initial area. So this will be a naught, and 1 plus this 2 will get multiplied with this alpha using binomial expansion. So your final expression will be this related to length and breadth. Let's say this is equation 2. Now just compare equation first and second and try to define relation between alpha and beta. So Mahira, what we can conclude using this, just compare each part in equation first and second. We have an A in left hand side for both equation, A naught as coefficient of that bracket in both equation. So in first part, delta t having coefficient beta, in second part, delta t having coefficient 2 alpha. So we can say on comparing equation first and second, this beta must equals to this alpha. Is it clear?
Yes, sir.
So we can say from equation first and second, on comparing each part, beta equals to 2 times of alpha or alpha equals to beta by 2. Asma, is it clear? Aisha, any doubt?
No, sir.
Okay, just write it down.
Done, sir. Done, sir. Done, sir.
Sakshi, done?
Yes, sir.
Nahara, any doubt?
No, sir.
Okay. Now related to this part, let me give you a question. A circular disc having coefficient of expansion along its radius is 2 into 10 to the power minus 4 Kelvin inverse. Find fractional change in area on changing temperature by 100 degrees Celsius. Let me define you how to solve for this part. In this question, we have coefficient of expansion of radius. And radius will be treated as one-dimensional quantity. So this particular term, 2 into 10 to the power minus 4, will be nothing but alpha. So according to this question, we have alpha equals to 2 into 10 to the power minus 4 Kelvin inverse. Now, according to the above relation, we may find beta according to this part. Now, next is we have to calculate fractional change in area. So beta equals to delta A divided by A naught times delta T. So from this part, delta A divided by A naught will become beta times delta T. Calculate beta from this alpha, and we have temperature difference 100 degrees Celsius. Put this in this part, you will get fractional change in area. Try to solve. Good, Samira.
So can you please do this question one time?
Okay. We have alpha. So according to the above equation, we can find beta as beta equals to 2 times of alpha. Okay, Aisha? So alpha is 2 in 10 to the power minus 4. So you may write 2 into 2 into 10 to the power minus 4. So this will become 4 into 10 to the power minus 4. Is it clear?
Yes, sir.
Now we have temperature difference of 100 degrees Celsius. Put this in this expression. Beta is 4 into 10 to the power minus 4 and temperature difference is 100. We may write it as 10 to the power 2. So on simplifying, you will get 10 to the power minus 4 plus 2. It will be 10 to the power minus 2. Is it clear?
Yes, sir.
Asma, any doubt? Sakshi, is it clear?
Yes, sir.
You all have done?
Yes, sir. Done.
Nahra?
Yes, sir.
Okay. Related to this aerial expansion, let me define you question. Suppose you have a rectangular sheet in which there is a hole at this point, another hole at this point. Let's say there is a point A, B, C, and D at some initial temperature T0. So on raising temperature, how will separation between A and D, B and C be affected? Just think. Sakshi, any clue what will happen?
No, sir.
Samaira?
So, the separation will increase between A and D.
Between A and D for first part.
Yes, sir.
And what about for second part?
Maybe they will come closer.
Okay. Let me define you. For this particular hole, initially, there will be a particle placed at boundary of this hole like this. So on heating, there will be weakening of bond. So separation between particle increases. So will it expand or contract on heating? So you will say, since separation between particle increases, so it will tend to expand. So it may acquire this type of configuration. Is it clear? Samaira?
Yes, sir.
Now, let's say between B and C, there will be n number of particles stacked one over one another like this. I'm considering just between B and C. So what will happen on increasing temperature? Will the separation between particles increases between B and C or decreases? You'll say on increasing temperature, bond gets weakened, so separation between particles increases. So they get separated to this point. So B will move to this point and C will move to this point. So we can say separation between B and C increases. Is it clear?
Yes, sir.
And since separation between B and C is increasing, so separation between A and D must be increasing as well. Is it clear? So both between A and D and B and C, separation will increase. So just remember, hole and its cutout portion both will expand at same rate on increasing temperature. So separation between particle on increasing temperature will increase in each case. Sakshi, is it clear?
Yes, sir, it's clear.
Nahra, any doubt?
No, sir. So, can you please explain the second part once again?
Okay. Suppose we have n number of particles stacked between B and C. Let's say from this point to this point, we have n number of particles. So if you raise temperature, just behave between B and C as linear object or may have linear configuration of these points. So on increasing temperature, separation between particles increases due to weakening of bond. So each separation on increasing will tend to acquire this particular type of configuration. So we can say separation between B and C increases on increasing temperature. Is it clear now?
Yes, sir. Thank you, sir.
And similarly, on increasing separation between B and C, so there will be separation between A and D as well.
Okay.
Okay, you all have written?
Yes, sir.
Asma, any doubt? Yes, Asma, you're not audible. Next is volumetric or cubical expansion. Suppose you have a cuboid having initial dimension L0, breadth B0, and height H0. So if you increase temperature of this particular object, there will be change in dimension along its all side. So length will expand, breadth will expand, and height as well. So in total, volume of this particular object will expand to this point. So new length of object will become L, breadth B, and height H. So to calculate volumetric change, we may define another coefficient of expansion as gamma. So it is called temperature coefficient of volumetric or cubical expansion. As we have defined beta above, which defines a rate at which area will expand or contract with change in temperature, similarly, gamma will define you the rate at which volume of this object will change. So it defines the rate of change in volume with respect to change in temperature. So we may write this gamma equals to fractional change in volume to the change in temperature. So this particular term is fractional change in volume and delta T is change in temperature. So gamma is the ratio of fractional change in volume to the change in temperature. Now, according to this formula, its SI unit will Kelvin inverse or degree Celsius inverse. Samira, is it clear?
Yes, sir.
Okay, just write it down.
Done, sir.
Done, sir.
Nahara, you have written?
Yes, sir.
Shika? Sakshi?
Done, sir.
Okay. So if you expand this particular relation, Gamma equals to delta V divided by V naught times delta T. Move this denominator to left side. So delta V will become gamma V naught delta T. Delta V is difference of volume. So it will be final volume minus initial volume equals to gamma V naught times delta T. Move V naught to right side. So new volume will become V naught gamma V naught delta T. Now take out V naught as common. So you are left with 1 plus gamma delta T equals to final volume. So this will be our final expression of getting volume at any change in temperature delta T. Okay, just write it down.
Done.
Done, sir.
Arslan, is it clear? Nahara, any doubt?
No, sir.
Okay. So similarly, we have to find relation between alpha and gamma. So relation between alpha and gamma. So we may write as volume equals to V naught 1 plus gamma delta T. Let's say this is equation first. To define the volume of a cuboid, we must need 3 dimension, that is length, breadth, and height. So take individually. Length equals to L naught 1 plus alpha times delta T. Since length is one dimensional, so it will depend upon alpha. Similarly, breadth is also length, so it will be 1 plus alpha times delta T. And height, h naught 1 plus alpha delta T. Now, if you multiply these 3 different quantity, you will get volume. So on multiplying length, breadth, height, L naught 1 plus alpha times delta T, breadth 1 plus alpha times delta T, and height 1 plus alpha times delta T. Now just combine them. L naught, B naught, H naught, 1 plus alpha delta T. We have 3 different times. So each having exponential 1. So on combining, it will become raised to 3. Now, according to binomial expansion, we may write it as length, breadth, height will be final volume. L naught, P naught, H naught will be initial volume. So V naught, and according to binomial expansion, this will become 3 times alpha delta T. Let's say this is equation 2. Aisha, is it clear?
Yes, sir.
So on comparing equations first and second, what we can conclude about alpha and gamma?
Gamma is equals to 3 alpha.
Good. So from equation first and second, on comparing, we can say gamma equals to 3 times of alpha, or alpha equals to gamma by 3. So we have calculated alpha in terms of beta. We have calculated alpha in terms of gamma. So on combining these three together, we can write alpha, since it is one-dimensional, so divide by 1. Beta, since it is two-dimensional, so divide by 2. Gamma, three-dimensional, divide by 3. These three will be equal like this. Now, take the LCM of this denominator and multiply each term. So you'll get 6 alpha, 3 beta, and 2 gamma. So this will be a relation between alpha and beta gamma together. Nahara, is it clear?
Yes, sir.
Okay. Sakshi, any doubt till this part?
No, sir.
Okay. Just write it down.
Done, sir.
Done, sir.
Sakshi, done? Asma? Okay. If temperature coefficient of area is 6 into 10 to the power minus 4 Kelvin inverse, find gamma and alpha. Use the above relation and try to find Good, Samira. Since we have in this part coefficient of areal expansion, that is beta. So we have beta equals to 6 into 10 to the power minus 4. And we have a relation between alpha and beta as alpha equals to beta by 2. Just put the value of beta in this part, you'll get alpha. And on getting alpha, gamma equals to 3 times of alpha. So you'll get gamma. So beta is 6 into 10 to the power minus 4 divided by 2. So it will become 3 into 10 to the power minus 4 Kelvin inverse. And then gamma is 3 times of alpha. So it will become 9 into 10 to the power minus 4 Kelvin inverse. Asma, is it clear? Aisha, any doubt?
No, sir.
Okay. Nahara?
Yes, sir.
Okay. If temperature coefficient of volumetric expansion is 4 into 10 to the power minus 4, so find change in temperature so that volume of body changes by 0.5%. Just use the above formula and try to find change in temperature. In this question, we have percentage change in volume as 0.5%. We may write it as delta V by V into 100 as 0.5. So from this, you may write delta V by V equals to 0.5 divided by 100. Now you have value of gamma. So you may write gamma equals to delta V divided by V times delta T. Since we have to calculate delta T, so move it to left side and rest of the quantity towards the right side. So just put the value of this part and this part and simplify it. Aisha, you got the answer?
No, sir, I'm doing.
Asma? Just see, we have delta V by V as 0.5 by 100. And gamma is 4 into 10 to the power minus 4. So we may write, move this 10 to the power minus 4 to numerator. So it will become 0.5 into 10 to the power 4 divided by 100 into 4. Now move this decimal. So you'll get 10. Now divide it. 5 divided by 4, it will be 1.25. 10 to the power plus 4 divided by 10 to the power plus 3. So you'll get 10 to the power 1. So on solving, you will get 12.5 degrees Celsius. Samira, is it clear?
Yes, sir.
Asma, any doubt? Okay, you all have written? Arslan? Sakshi, done?
Yes, sir.
So this is all about expansion of solid in one-dimensional, two-dimensional, and three-dimensional. Now, on the basis of this expansion, let me define you its effect on density. So next is temperature dependency on density of body. Let's say at temperature T naught, density rho naught equals to mass divided by volume. Aisha, will there be any change in mass of a body on changing temperature, or it will remain same? Samara, will there be any change in mass on changing temperature?
No.
Good. So on changing temperature, dimension of body changes, and consequently density of body will change, keeping mass to be constant. Good, Aisha. So we can say mass of body remain unaffected on changing temperature. So at temperature T, final volume will become V naught 1 plus gamma delta T. So on increasing temperature, volume of object will increase. So if you put in the above expression, you will get rho equals to mass divided by volume, mass divided by V naught, 1 plus gamma delta T. Mass divided by volume is nothing but initial density. We can write it as rho naught. So rho equals to rho naught divided by 1 plus gamma delta T raised to 1. Now move this denominator to numerator. Its exponential will become minus 1. So you'll get rho naught 1 plus gamma delta T raised to minus 1. Samira, is it clear?
Yes, sir.
Now, according to binomial expansion, we may write this minus 1 get multiplied with its coefficient. So gamma will become gamma naught 1 minus gamma rho equals to rho naught 1 minus gamma delta T as final expression of density. So we can say this minus sign will define on increasing temperature, density of body will decrease. Is it clear?
Yes, sir.
Okay, just write it down to this part. Nara, is it clear?
Yes, sir.
Okay.
Done, sir.
Arslan, you have written? Asma, done? Okay. Try to solve if density of mercury at 0 degrees Celsius is 13.6 gram per centimeter cube. Find its density at 50 degrees Celsius if gamma is 4 into 10 to the power minus 4 Kelvin inverse. Just use the above formula and try to find we have initial temperature T0 to be 0 degrees Celsius. Final temperature T is 50 degrees Celsius. So take difference of this two part to find delta T. Initial density is 13.6 gram per centimeter cube and gamma is 4 into 10 to the power minus 4 Kelvin inverse. Use the above expression to find new density, rho. Samira, just check your calculation. There is 1 minus gamma delta T. Let me solve. New density rho equals to rho naught 1 minus gamma delta T, in which rho naught is given as 13.6. 1 minus gamma is 4 into 10 to the power minus 4, and change in temperature is 50 degrees Celsius. So if you difference these two temperature, 50 minus 0, you'll get 50. So on multiplying 13.6, 1 minus 5 into 4, 20. So it will become 0.02. So 13.6 into 1 minus 0.02, it will be 0.98. So if you multiply this part, you will get approx 13.3 gram per centimeter cube as final density. Aisha, is it clear?
Yes, sir.
Samira, is it clear?
Yes, sir.
Asma, any doubt?
So 13.6 minus 0.98, right?
It is 1.1 minus 0.02. So we may write 1.00 minus of 0.02 like this. So 10 minus 2, it will be 8. 9 minus 0, it will be 9 like this. Okay.
Okay, okay, sir.
Sakshi, is it clear till this part?
Yes, sir.
Okay. You all have written?
Yes, sir.
Yes, sir.
Nah. Nahara?
Yes, sir.
Okay. In this part, density is decreasing on increasing temperature, but there will be exception in case of water. Let me define you, which is called anomalous behavior of water. Volume versus temperature. Correspondingly, density versus temperature. If temperature is changing from 0 degrees Celsius to 4 degrees Celsius. In this range, it will behave differently. Volume will decrease, correspondingly, density will increase. Let's say this is 4 degrees Celsius. So at 0 degrees Celsius, it will have more volume. On increasing temperature, its volume will decrease to this point. Correspondingly, density will increase due to decrease in volume like this. And on further, 4 degrees Celsius and above, volume will increase with rise in temperature and correspondingly density will decrease due to increase in its volume. So it will start increasing and correspondingly it will start decreasing. So this temperature is 4 degrees Celsius. This behavior in water will be due to hydrogen bonding, which may behave differently in this particular range. Now, according to this behavior, which facilitate the existence of aquatic life in ocean, let me define you. Suppose this is surface of water. So on decreasing temperature and surrounding, water will start freezing from its top surface. Since it is exposed to atmosphere first, so it will get cold energy first and then freezes. This particular formation of ice will further act as shielding to the lower portion of water. And inside it, water will remain above 0 degrees Celsius, 1 degree, 2 degrees Celsius, or 4 degrees Celsius. Since water having temperature more than 0 degrees Celsius will have more density as compared to ice at 0 degrees Celsius. So it will remain towards downward side and facilitate existence of or movement of aquatic life into that. Is it clear?
Yes, sir.
Samaira, any doubt?
No, sir.
Okay. So the above formula is exception in case of water between 0 degrees Celsius and 4 degrees Celsius. Just write it down.
Done, sir.
Asma, done?
Done, sir.
Sakshi, you have written?
Yes, sir.
Okay. So this is all about the first part of this particular chapter, that is expansion and its different behavior. So let's stop here for today. In next class, we'll start new topic, that is calorimetry, the exchange of heat between two different bodies or system, which results in the change in their temperature or change in their state. Okay. So just revise this whole part and try to do more problem related to this. Okay. We'll continue in next class.
Thank you, sir.
Thank you.
Thank you, sir. Bye, sir.
Oh, thank you.